Father, we thank you for today. Thank you for your mercies. Thank you for your love. Blessed be your holy name. As we start, Holy Spirit, we ask and pray your presence start with us. Give us understanding, wisdom, knowledge, and speed. In Jesus' name. Amen. All right.
Amen.
We'll be starting today. In our previous class, we got to understand, we started off with simple harmonic motion, and we started off with some definition of some terms in simple harmonic motion. We started off by describing the amplitude, that the amplitude is the maximum displacement from the equilibrium position. Okay. We also talked about the period T, which is the time taken for the body in a simple harmonic motion to complete one oscillation. Okay, we also got to tell you that the period T is given as small letter t over n, and which it has an SI unit in seconds. We also spoke about frequency, which is the number of cycles completed by a body in 1 second. We know that frequency is measured in hertz, or we can also call it per second. Now we did mention angular frequency, which is the ratio of one complete cycle to the period of the simple harmonic motion. I did mention that angular frequency is sometimes referred to as angular speed, and we talked about displacement. Okay, we started solving some questions, some simple questions. I believe I also did mention that at the midpoint, your x is 0, because when we're asked to find, in one of our questions, we're asked to find the velocity acceleration at the middle, and we said that maximum acceleration, maximum velocity happens when x is 0, and that is at the center of the motion. Happens when x is 0 and at the center of the motion. And we said that minimum velocity occurs at the extreme position, and that is only when displacement is equals to the amplitude, which the same thing happens to what do you call it? The same thing happens to acceleration. Okay, for today, let's see. Have we talked about angular acceleration? Have we talked about angular acceleration? I guess we haven't done that, right?
No.
Okay, let's start with angular acceleration.
But you gave me some formulas that I should write it down.
Okay, let me share the screen. Can you just write the formula so I know which of the formulas I was talking about? All right, this is one of the things I asked you to write, but sorry, what's this? But this square root was actually the total square root. It was actually a total square root. And this m also was also a total square root of m and k. All right, I think what I wanted to explain why I asked you to write these formulas was because of angular acceleration. I guess this was angular acceleration. I wanted to explain. Okay, let's write angular acceleration now. The angular acceleration of the body, which is the angular acceleration of the body A, is the time rate of change of its angular velocity is the time rate of change of its angular velocity. It is expressed in radian per second. It is expressed in radian per second. So that means what we're trying to say is that, okay.
So please can you repeat it?
Okay, the angular acceleration of a body, which is the angular acceleration of a body, is the time rate of change of its angular velocity. It's the time rate of change of its angular velocity. In other words, what we're trying to say is that is the change in angular velocity over time. The change in angular velocity over time. That means the change in angular velocity, which is exactly what you had there. Change in angular velocity over time. So that is the angular acceleration. So this is actually the angular acceleration. Okay. Now there's a correlation between the linear acceleration and the angular acceleration, and that is what we have the formulas. A is equals to, A is equals to this times the R, which is linear acceleration is equals to the product of the angular acceleration times the radius, which is also, you can also call that the displacement of the particle from its central position. So there's a correlation, like I said, between the angular acceleration and the linear acceleration, just the way we had angular velocity and linear velocity. Also, there's a correlation between the angular acceleration, and this is the linear acceleration, which is equal to the product of the angular acceleration multiplied by the radian. Remember, we know that maximum acceleration occurs when x is at that means when x is equal to 0 and at the middle. Let's see a question. Let's just have a simple question before we want to do something that has to do like a practical. Now, let's do this. A body executing simple harmonic motion, at an angular velocity of 22 radian. Have we done that before, please?
No, sir.
Let's do it then. All right, I said a body exhibiting simple harmonic motion at an angular velocity of 22 radian. Okay, this is it. Okay, I believe it's something you can try out. Okay, where you have any issues, please. Now, this is what they said. A body executing simple harmonic motion has an angular velocity, remember, of 22 radian. Okay. per second. If it has a maximum displacement, of 10 centimeter, okay, let's convert this to meter. That becomes 10 over 100, isn't it? And that gives us 0.1 meters. What is the maximum linear velocity? That means we are looking for V. Remember, there's a relationship between V and between the linear velocity and angular velocity, which we have as V is equals to the W, the square root of what? A square minus X square, isn't it? Right? Okay. Now, they said something here that V, what is the maximum linear velocity? When is velocity maximum? Remember, I did mention earlier today that velocity is maximum when X. Velocity is maximum when X, that means we have Vmax. Vmax occurs when X is equals to 0, isn't it? Now, if X is equals to 0, that means we have V is equals to angular velocity, the square root of A square minus 0. And that gives us V is equals to angular velocity multiplied by, then this gives us the square root of A squared. Remember, we're having square roots and the square. In indices, we understand that when we have both of them together, they cancel themselves. This can be written as multiply by 1 over 2, because square root is 1 over 2. That's raised to the power of 1 over 2. Then this cancels this. That means the formula becomes, when V is maximum, the formula becomes angular velocity times A. Okay, now we apply the formula here. That becomes Vmax equals to angular velocity A. We have the angular velocity as 22, and we have the A as 0.1. That gives us what? 2.2 meters per second. I believe you understand that. Hello?
Why did you multiply the S square by
Sorry?
half?
You said what, please?
So why do you multiply the A square by half?
Okay. In
A
indices,
square.
okay, in indices, this is what happens.
So why did you multiply the A square by half?
Okay. In indices, this is exactly what happens. Come in, please. In indices, when you have square root of A, is the same thing as A raised to the power of 1 over 2. Just the same way when you have cube roots. When you have cube roots of A, is the same thing as A raised to power 3 over 2. So when you have the square root of anything, the square root of anything is the same thing as raised to the power, the square root of. I said that when you have square root of A in indices in mathematics, is the same thing as a raised to the power of 1 over 2. When you have the cube root of a, same thing as a raised to the power of 3 over 2. Now, square root is seen the same thing. That's why when we have roots of a multiplied by roots of a, it's the same thing as a raised to the power of 1 over 2 multiplied by a raised to the power of 1 over 2. Now that gives you a raised to the power of 1 over 2 plus 1 over 2. That's in indices. And that becomes a raised to the power of 1, which is a. That's the reason why when you have in your calculator, when you have root 3 multiplied by root 3, you have it as the answer is 3, because it obeys that law that when you have roots of any number, when you have the root of any number, it gives you, when you have the root of any number multiplied by the root of another number, it gives you the value of that same number. Do you understand that, please? Hello? Like I said we're going to see how to do some practicals, experiments on simple harmonic motion. Why I would want us to do this here, it's when you start doing that, you would notice that you will start having to do that in your exams, your practical. And since we're online, I would want to see how I can explain the simple harmonic motion experimentally, if possible, watching some videos on that also. So it makes us understand. So when you have to do the real life practicals, you have an idea of what we're talking about. So let's see an example of what we can do, one of the practicals in simple harmonic motion. Now, what we do is we make use of sometimes or most times a pendulum. Can you hear me, please? Most times we make use of a simple pendulum. Now, the simple pendulum is tied most times to a small ball of heavy metal and then with a light spring. Now, what we used to do is we use it to determine the value of the acceleration due to gravity. Now, one of the things we do is, number one, we tie one end of the hook then to the simple pendulum and then measure using a meter rule. Okay, using a meter rule, we are going to be giving the length in centimeter. Okay, we have from 100, 90. What we want to see, we are going to measure the number of oscillations using the simple, with your stopwatch. We're going to look at, we're going to see the number of oscillations it moves. All right, from here, I'll be showing you an experiment online. I'm going to be showing you an experiment using a video to see how it's been done. Then we can understand it better off from there. Let's see how it goes from here now.
Hi, it's Mr. Reese here from Raspberry Science.
Okay, I'll be sharing this now.
And I'm going to show you how to do the A-level physics required practical.
Can you see this, please? Can you see this? Okay.
Hi, it's Mr. Reese here from Raspberry Science, and I'm going to show you how to do the A-level physics required practicals on simple harmonic motion for a simple pendulum and a mass spring system. With the pendulum, what we want to do is change the length of the string, and then we're going to measure the time period of its oscillations. Now I've used a couple of pieces of wood to clamp the string in between, because if it was just hanging over something, then that means that the pivot wouldn't be fixed. So I can be sure that the pivot is right at the bottom of these pieces of wood. Now when we measure this, we want to be fairly accurate, and so you'll need a centimeter resolution or 1 millimeter resolution ruler. I'm going to use a meter rule here. Now I've got mine set up here for 30 centimeters, so I'm just going to check that that's correct. Notice that I'm measuring from the bottom of the wood to the middle of the bob. That's to make sure that I'm measuring to the center of mass, not to the top of the bob or the bottom of the bob. You can choose what length to do. I would go from 10 centimeters all the way to 100, and you'll need to hang your pendulum off the side of the table in order to do that, but that's okay. Now the thread that I've used is light and is inextensible as well. Now, do that, but that's okay. Now the thread that I've used is light and it's inextensible as well. Now in order to make sure that we are being as accurate as possible, I'm going to use a nail as a fiducial marker, and I'm just going to pop that on here, and that's going to be very close to the string, although not touching it, and you don't want it too close because the string will move sideways a little bit as well, and it could catch it like that. What you want to do is line up your nail so it's directly behind the piece of string when the pendulum is at equilibrium. Then you want to get on eye level, and so if I was doing this experiment, I would have my pendulum there, and I'd be looking at eye level so I can be sure when the string has gone at equilibrium. So I'm going to displace the pendulum. Now we're going to do it about 10 degrees. We don't want to do it up here. The bigger our amplitude, the less accurate the equation T equals 2 pi root L over G is. So I'm just going to displace it this much. Doesn't need to be much at all. But we can just set it going. And just to be clear, one oscillation is now to now. It's not from one side to the other. It needs to go there, back, and to the center again. So I'm going to start my stop clock when it passes equilibrium next. And obviously I would want to be at eye level with the fiducial marker if I was doing this for real. I could measure the time taken for one oscillation, but that's not going to be accurate. So I'm going to measure the time taken for 10 oscillations, then average it. Don't forget that when you start your stop clock, that's 0, and then you're counting 1 after that. So here we go, starting my stop clock now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Naked.
So, did you understand what he did there now? Did you understand that?
No, sir.
Okay, and let me explain what he said. This is exactly what happens. This is exactly what happened there. You used a retort stand. This is a retort stand. We are using a simple pendulum. Remember, it goes from left to right, from left to right. Now, this is a stopwatch. He's going to use a stopwatch. Now, he measured the length because that brings us to that formula I gave you of 2 pi, the square root of L over G here. Okay, now this is, we want to calculate the time. When we have the period, when we have the time and the length, we use a formula like this. Now, but we are going to perform the simple experiment using a simple pendulum. You can actually use a simple pendulum or a mass suspended on a spring. Now, for the simple pendulum, this is exactly what he does. This is exactly what he does. He brought the, he tied it down with a rope, measured the length. I guess he used 100 centimeter. That is a 1 meter rule. He used 100 centimeter, measured it, the length to this place. Now, after measuring it, another thing you must understand is the oscillations. Oscillations occurs when it has gone, probably if you held it here, if it moves, look at what I just did now. Look at this place. Remember when he held the bob moved from here to here. Now, this is how you calculate your oscillations. Your oscillations goes from, if you start it from here, now when it has gone here, if you started it from probably the right-hand side, if you started it from the right-hand side, this is actually what it does. If it has moved from the right to the left, can you hear me?
Yes, sir.
Okay, this is how it goes. When it has moved from the right to the left, and it comes back to the right, that is one complete oscillation. So that is why you saw what he was doing. He was calculating, he was counting it, that if it has gone from here to here, coming back again, that is one oscillation. Move from here to here, come back again, that is two oscillations. So you don't count from left to right as one oscillation. No, you don't count from left to right as maybe two oscillations, that it goes from left, right, 1, 2, 3, 4. No, that's not how it's being done. How you calculate it is that it goes from left to right, then it comes back to the left, that is one oscillation. Goes back, come back again, that is two oscillation. Go back, come back again, that is three oscillation. Remember when we're calculating time of flight in projectiles, I mentioned to you that the time it takes for the projectile to go and come back, that is the time of flight. That's the total time of flight. Remember that, right? I believe you remember that. Okay, now that is exactly what we do.
Yes, sir.
Okay, the time it takes to go and come back, that is one complete oscillations. So that's exactly what he was doing here. I believe you have you understand that now.
Yes, sir.
Okay, let's see this now. Let's see it again.
To the other, it needs to go there, back, and to the center again. So I'm going to start my stop clock when one oscillation is now to now. It's not from one side to the other. It needs to go there, back, and to the center again. So I'm going to start my stop clock when it passes equilibrium next. And obviously I would want to be at eye level with the fiducial marker if I was doing this for real. I could measure the time taken for one oscillation, but that's not going to be accurate. So I'm going to measure the time taken for 10 oscillations, then average it. Don't forget that when you start your stop clock, that's 0, and then you're counting 1 after that. So here we go, starting my stop clock now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that gives me a time of 11.56 seconds. Dividing that by 10, that means that one oscillation, the time period T is going to be 1.156 seconds. I then want to change the length and do the same again. So here are my time periods for all my different lengths. I've just gone 20 centimeters, 40, 60, 80, 100. Now the equation, like we said.
Okay, look at this now. The length, look at the length, look at what happened here now. He used 0.2. He used 0.2 as the length. That's 20 centimeters, because this is meters now. So this is 20 centimeters. Okay, and when he calculated it, the time, remember he did that for 10 oscillations. 10 oscillations. And then from the stopwatch, he got 8.9. Now dividing it by 10, because of acceleration due to gravity, he got 0.892. Now he did that for 40 centimeters. Did 10 oscillations. Remember the oscillations I told you? It must be from left to right. It comes from left to right to left again. That's one oscillation. Left to right, comes back again to left. That's two oscillations. Remember that? Now dividing it, it got 12.43. Dividing it by 10, it got 1.243. Like that, till we got to 100 centimeters. 100 centimeters, 19.94, and it got 1.994. I believe you understand this part, right?
Yes, sir.
Okay.
Is t equals 2 pi root L over G, where L is the length of the piece of string. So we can't draw a graph of t against L because they're not proportional. Squaring the whole equation, though, we can see that t squared is proportional to L. So that's what we're going to draw on our graph. T squared on the y-axis.
Okay. Now, he used this formula, squaring them, he used this formula, and that gives us t squared. T squared is equal to 2 pi square L over G. Now, he got, what he did now was to plot a graph, because what you'd be required to do would be plot a graph of t squared against L. Plot a graph of t squared against L. So this is t squared. Sorry, this is L, and this is t squared. Now, when you plot the graph, what you'll be having actually, it's a straight line graph, a graph going ascending. So this is the kind of graph you'll be having. Now, why I actually went through this is because, so you have a vague on this, you have a clear understanding of what you'll be required to do, even though we are not doing the practical because of distance now, but at least you should be able to know this is what will be required of me when I want to do this kind of practicals. Or if probably you were meant to do GCE, where you be meant to do, or where you be required to do alternative to practicals. So you know, okay, this is how I get my result. This is how I got my result for 10. This is how I got my, that's divided by 10. This is how I got my result for t squared. As long as you can get, you know, your 2 pi L over G, you know your length, you know your gravity, you can actually get your t squared. All right, let's continue, please.
And L, length of the piece of string on the x-axis. Finding the gradient, that is equal to, according to the equation, 4 pi squared divided by g. So what I can do is verify this relationship by finding g. Just swapping gradient and g over, we end up with g equals 4 pi squared over the gradient. And if I wanted to, I could find out the percentage error in that compared to the accepted 9.81 meters per second squared. The mass spring system is very similar. All we have to do is get a spring, and what we can do is...
Now he wants to do the mass spring. Remember I told you in calculating simple harmonic motion, there are two things we can use. We can either use the mass spring system. That's when you're using a mass, it has to be suspended on a spring. And if you're using a simple pendulum, we can use a thread. So he wants to do the second part, which is the mass spring system. The mass spring system. Do you understand what I'm saying?
Yes, sir.
Okay.
Trap it on the arm of a clamp. And we're going to have a nail as a fiducial marker, as per usual. Let's start with 100 grams of mass on the end of the...
Now, what I said was any zero error of stop clock should be noted. Any zero error of stop clock should be noted and taken into account. Any zero error of stop clock should be noted and taken into account. So I'm going to go through the precautions again. I said, number one, the total length of pendulum should be measured from the rigid support to the center of the bulb. Number two, the pendulum should be made to oscillate through a small angle. Number three, that the bulb should be made to swing freely without gyration. There should be no external force. And because of that, that leads us to number four, which says that drought should be avoided. Such as switching off of moving fans, closing of any barriers, and where we have much intrusion of air. And the last one is any zero error of stop clock should be noted and taken into account. Get all of that, please.
Yes, sir.
Okay, awesome. So we now know the formula. When we have simple pendulum that has to do with the length of a spring, the length, and if it has to do with mass, we know fully well that for mass, we have something different of 2 pi. So you now see the purpose of the formula I gave you. Over k, that's the force constant. All right, this leads us to the next. This leads us to the next thing we'll be discussing. I'm coming. Okay. All right, I believe we have just done a very good thing. Remember we said at the middle, at the center, speed is maximum. Okay, please just write this as a note, as notes. At the center of any simple harmonic motion, speed is maximum, kinetic energy is maximum, potential energy is 0. At the center, that's at this place, at the center of any oscillation or a simple harmonic motion, speed is maximum, kinetic energy is maximum, while we have potential energy is 0. And that brings us to what we call the energy of a simple harmonic motion. Energy of a simple harmonic motion. Energy of a simple. Now, let's come to this now. Now, from this place, looking at the energy of a simple pendulum, one of the things we know about is that when a body is in simple harmonic motion, undergoes displacement as a result of its restoring force acting on it towards the equilibrium position. Energy is always involved when a body moves from a distance under the action of force. Okay, and now that brings us to this. We know from this end, from the end, or from the beginning or the end of any simple harmonic motion, PE is always maximum. That's the potential energy is maximum, and that's mgh. And velocity and kinetic energy is 0. Is 0 because at that point there is no motion, there is no movement. At that point, at the beginning and at the end, when it comes to rest, at that point, potential energy is maximum. But when it is at the height of the motion, that's at the center of the motion, potential energy at that point is 0, kinetic energy is maximum, and velocity is also maximum at that point, at the middle, because at that point, that is when it is moving. So, and at the end, so we need to understand that at the end, at the beginning, at the end of any simple harmonic motion, what happens is that potential energy is maximum, while kinetic energy is 0. So the total energy now for a simple harmonic motion, maybe that's the maximum total energy stored in a spring or in a simple harmonic motion is half Ka squared. Now half Ka squared, where K, now please write this, where A is the amplitude of motion, where A is the amplitude of motion, or where A is the amplitude of motion or maximum displacement from equilibrium position, or maximum displacement from equilibrium position. And K is the force constant of the spring. K is the force constant. K is the force constant of the spring.
Yes, sir.
Sometimes when we examine the motion of an object, it will involve a single action, like a rock falling from a cliff down to the ground. This will probably just happen one time, after which the rock will remain at rest. But some motion is periodic, meaning repeated, like the motion of the pendulum on a grandfather clock, or the vibration of a spring. We will refer to this kind of motion as simple harmonic motion. Say we have a spring that is attached to some stationary surface, and on the other end of the spring, there is a block of a particular mass. If we pull this block so as to expand the spring, and then we release the block, it will vibrate back and forth between more compressed and less compressed states. If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or least compressed, and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest. If we were to graph the position of the block against time, it would display sinusoidal behavior, just like a trigonometric sine function, where the block continues to occupy the same positions over a particular period of time, which is why we call this periodic motion. X equals 0 at the equilibrium position of the block, where it sat before we pulled it, and assuming zero friction, the block will oscillate between positive X and negative X indefinitely. In reality, frictional forces will dampen the spring's activity, and it will eventually come to a stop. But for many systems, an ideal mass spring system will be a decent approximation for a real one. Of course, every spring is different. Some are loose, like a slinky, and some are stiff, like the spring that launches a pinball into play. This factor is represented by the spring constant K, which will be unique to a particular spring. The force that a spring can exert is equal to negative K times the displacement of the object it acts upon, and this relationship is called Hooke's law. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. When the object compresses the spring, it will push out, and when the object stretches the spring, it will pull in. In both cases, the spring is attempting to move the object back to its equilibrium position, which is why the force applied by the spring can be called a restoring force. The units on a spring constant will be newtons per meter, so that when you multiply by some distance x, you get the force that must be applied to compress that spring that far. Let's also note that the elastic potential energy of a spring will be equal to 1/2 kx squared, where k is the spring constant and x is the distance it is stretched or compressed. If at equilibrium, the distance is 0, so it has 0 elastic potential energy, and the maximum elastic potential energy will occur at the maximum distance from this point on either side of the oscillation. This expression looks similar to the expression for kinetic energy, which is convenient since the two will interchange as the mass oscillates. A pendulum also displays periodic motion since it swings back and forth between the same two positions. Although this involves gravitational potential energy rather than elastic potential energy, and we will look at this behavior next. Let's check comprehension.
Can you try this? Hello? Okay, I believe you can understand. This is actually from Hooke's law. It's actually from Hooke's law. Okay, now let's solve a question that has to do with simple harmonic motion. Please write this question down. A body of mass 20 gram is suspended from the end of a spiral spring. A body of mass 20 gram is suspended from the end of a spiral spring whose force constant is 0.4 Newton per meter. Newton per meter. A body of mass, sorry, can you hear me?
Yes, sir.
Now, this is the question. A body of mass 20 gram is suspended from the end of a spiral spring whose force constant is Newton per meter. All right, the body is sent into a motion with an amplitude of 0.2 meters. Calculate A, the period of the motion. B, the frequency of the motion. C, the angular speed. D, the total energy. I want you to solve these questions. I believe there are some of them you should be able to do. Now, the question was a body of mass 20 gram. Okay, so we have the mass of 20 gram. Let's convert it to kilogram. That becomes 20 over 1,000, isn't it? Zero 0.02, right? Kilogram. Now, it's suspended from the end of a spiral spring whose force constant, the force constant hello, can you hear me?
Yes, sir.
Okay. The force constant in this case is 0.4, which is K, 0.4. All right. The body is sent into a superharmonic motion with an amplitude, that means an amplitude of A is equals to 0.2 meter. Now the question is find the period of the motion A. Let's get the period. Now, remember we have different formulas for period depending on the parameters we're given. Now, one of the formulas we can use for period is this. Now, look at what we're given. We're given just M, we're given K, we're given A. Which formula relates to MK? For period, we have T is equals to 2 pi the square root of M over K. All right? So that becomes 2 pi. So I need you to do this for me quickly. 0.142 times the square root of M, which is 0.02 divided by K, 0.4. All right. So is it something you can do? So 2 multiplied by 2 times 3.142 gives us 6.284. 6.284 multiplied by this, okay, 0.02 divided by 0.4. That's 0.05. So let's get the square root of 0.05, 0.05, and that gives us 0.24. 0 point times 0.2. Okay, let's use 0.224.
Yes.
0.224. Okay, so that gives us what? Times 6.284. Now that gives us 1.41. 1.41 seconds. You understand that, right?
Yes.
Okay. Now, if we have done this, the next thing to do is they said B. They asked us to find, okay, the frequency. To get the frequency, that gives us frequency is 1 over T, and that becomes 1 divided by 1.41. Okay? That's 1 divided by 1.41. That gives us 0.71. 0.71. Remember your units, very important. Hertz, or you can call it or per seconds. Okay. The next thing to do is find the angular speed. The angular speed, remember, is this is equals to, you can use 2 pi over T or 2 pi F. That you can use any of them, and that gives us, okay, that gives us 2 times 3.142 multiplied by 0.71. Okay, what's the answer, please? Okay, what's the answer? 2 multiplied by 3.142 multiplied by 0.71. That gives us 4.46. Since we are talking about angular speed, you can call meter per second, or we can call radian per second. The next thing we're asked to find is the total energy. The total energy. All right. I'm not going to do total energy for you, but you know, total energy, you can actually use the formula of half Ka square. Okay, half Ka square. Now that, okay, let me do that, don't worry. That's half K is where's that K? 0.4 multiplied by 0.2 or squared. All right? So 0.2 squared. Now everything would give us 0.8, 0.08, 08 joule. All right?
Yes, sir.
The next one is E, the maximum velocity. Remember I told you V max is equals to E. That's when X is 0. Okay, It has actually cleared my screen network. Okay, so what we do is, remember I said Vmax is, this is a when x is 0, and acceleration max, for acceleration max, we have it as minus w square a, right? So use these formulas to get your acceleration, your maximum acceleration, and your maximum velocity. Now, I'll be giving you, so what's your maximum acceleration? Can you do that and let me know quickly, so I can just give you an assignment? What did you say again, please?
3.978 meters per second square.
For what? What was that?
A max.
Okay, A max, that's 3.98, good, meter per second square. And what about your V max?
Yes.
What did you say?
0.892 meters.
Okay, awesome. 0.892 meter per second. Beautiful. All right. Now I'm going to give you an assignment just the way I did for last time. Now the mass now we'll be having is we'll be having a mass of 50 gram. So change the same question, but change your mass to 50 gram. Change your mass to 50 gram at the end of the spiral spring, whose force constant is, change it to 0.7. Your force constant would be 0.7. The body is set into a simple harmonic motion with amplitude of 0.4. Did you get that?
No.
Okay, I said a body of mass, change it to 50 gram. The same question, just change it to 50 gram. Suspended from the end of a spiral spring, whose force constant is 0.7. Change it to 0.7 Newton per meter. And the body is set into a simple harmonic motion with an amplitude of 0.4. 0.4. So you can, the other questions remains the same. Do you understand?
Okay. Yes, sir.
All right, let us pray now. Father, we thank you for today. Thank you for your mercies. Thank you for your love. Blessed be your holy name. In Jesus' name.
Amen.
Right. Any question? I hope you understand all.
Yes, sir.
Okay. All right. So we meet again tomorrow. All right. Bye for now.